So I want to be clear that I'll mostly be talking about excited states in semiconductor moiré superlattices. And I want to motivate, how we get to the twisted hBN work. And so first of all, let me start with acknowledgement. I have a lot of wonderful collaborators at the UT Austin, but the work I'm going to, especially the new work that I'm going to present to you, the work are led by 2 senior students in my group and supported by 2 younger students. And all of them are actually at this wonderful workshop. Please, maybe answer their questions patiently when you meet them. And they build on the work of senior students who already left and then move on to greater things. For most of the new result I'm going to present, I have some wonderful collaborators and theorists, and Li Yang and Yao Wang from Hong Kong, and a local scanning probe expert that really helped us to understand some critical measurement that we were doing to understand twisted hBNs. Okay, so I wrong orders. Everybody, I think moiré superlattice needs no introduction to this audience. Specifically, our group, myself, started my graduate studies and study excited state excitons in quantum dots. I initially visualized these states as an array of semiconductor quantum dots that can confine individual electrons, holes, or electron-hole pairs when we excite the system optically. And, also my early understanding of the system is very much informed by some beautiful STM work done by my colleague, Ken Shi, who's here in the audience. And he studied some CVD-grown TMD bilayer to begin with. These materials, as they're grown in the chamber, they tend to be aligned in the crystal axes. And but because the lattice mismatch in this particular combination of TMD that his group have studied, you have these moiré superlattice, and this particular image is actually topology measurement that shows that at the AA stacking, local stacking, the spacing between the 2 layers are the largest, perhaps that translate into weaker interlayer coupling at this particular local site. And then you would also have several other high symmetry stacking points, and then the bridge point between them. And importantly, his group used what's called the valley resolved STM measurement to articulate or to precisely quantify the local energy gap at the several high symmetry stacking point varies up to 200 MeV. And of course, this particular number will vary, depends on the particular bilayer sequence you chose. And it's not explicitly shown in these figures that I've chosen, is that the conduction band and the valence band maxima in these material may actually happen at different locations within the supercell. And this is important to one of the topics I'm going to tell you later on. Okay, so in the monolayers, the optical selection rule in these TMDs are rather simple. The excitons electron hole pairs tend to form at the boundary of the Brillouin zone or at the K prime valley. And these 2 valleys are related to each other by time reversal symmetry. Therefore, they couple to sigma plus and sigma minus light selectively. And there are a lot of early work to study valley polarization and valley coherence in these materials. The picture gets much more complex when we start to look at the stacked heterostructures. And for the next few slides, I'll be telling you a combination, particularly made of MOSE2 and WSE2. And these materials form what's called a type 2 band alignment in the heterostructure. When you put electron hole, either electrically or optically, into the bilayer, the electron tend to go to the MO layer and the hole tend to go to the tungsten layer. And as an optical excited state, you have both what's called the intralayer exciton that features very high oscillator strength, a short lifetime, and interlayer exciton where electron hole, loosely speaking, will preside in 2 separate layers, and they have much smaller dipole moment and very long lifetime. And the selection rule also becomes much more complicated, and as articulated in this first paper by Yao Wang here, if you were able to put excitons in spatially resolved manner, if I only keep track of the K valley, and there always will be a time reversal copy in the K prime valley, and at 3 high symmetry stacking point, you'd actually have sigma plus, sigma minus alternating selection rule And then the third point, you actually have dipole moment that's perpendicular to the plane. And therefore, not only in the moiré system, you will have a moiré potential modulation on the order of 200 MeV or higher. You would also have these pattern of circular selection rule for excited states. And to make the matter more complex, if you allow the thoughts, the idea that the moiré potential is deep enough, and even at the particular local point, you can host both the ground state and excited states. These transitions would also have alternating selection rules. And these selection rules are worked out by Feng Cheng and Alan around the same time. So in our early paper, we have chosen these ground state and excited state pictures for a variety of reasons, both depend on related to their dynamic property and also depend on their thermal temperature dependent property. But I won't want to elaborate on that too much. Just to say that this always our hard work of graduate students making a dozen samples and to find the highest quality ones. And these are the two early samples we studied with different twist angle. And there are multiple interlayer exciton transitions, and the energy spacing are indeed getting bigger in a larger twist angle because the lateral confinement is getting smaller, the energy spacing is getting bigger. And incidentally, we were lucky to find this alternating preferred selection rule in the PL. I would say the selection rule, especially if you want to observe it in PL, can get quite complicated. So it's not always easy to repeat such behavior because it's a very complicated dynamic competition process for recombination and value relaxation process. And when you write a review paper, even a year ago, a lot of this is already outdated. One more thing we noticed is actually the lifetime of the interlayer exciton very sensitively depends on the twist angle. And if we take one of the higher intensity photoluminescence peak, we analyze their lifetime, and we notice, in small twist angle, they have a lifetime about a nanosecond. That lifetime is close to material grown by CVD without any moiré pattern. But as soon as we increase the twist angle by 2 degrees, the lifetime can increase by almost 100-fold. It has a very simple picture to account for the leading order effect. Is the fact that when you rotate the moiré system in real space, you're actually also shifting them in a momentum space. So for the optical transition happening near the KK point, you're shifting the bottom of the conduction band away from the top of the valence band, therefore giving rise to a little bit of indirect transition nature, make the transition highly sensitive to the twist angle. And when you take into account the moiré effect, it actually relaxes this lifetime dependence a little bit. The fact that you have very long lifetime do make these interlayer excitons preferable perhaps to look for a condensate state and other properties. Diffusion, exon diffusion is heavily studied as well. Although we started with the picture that the electron hole and excitons are all localized by the moiré supercell, the reality is not so simple. Because the lifetime grows very quickly with the twist angle, we can actually start to see the exciton diffuse when we have sampled that with about 3.5 degree. I cropped the labels. This is actually 1 degree twist angle sample. Within the optical diffraction limit, we cannot observe any diffusion behavior. So this is our picture of how they are basically sitting at the bottom of the potential. But when we increase the twist angle, we start to observe the spatial diffusion behavior from these excitons. So this, I used maybe 5 minutes, and I'll see to summarize our early understanding of moiré excitons. They're of course subject to the periodic moiré potential. There are different type of excitons that follow complicated selection rule, and these excitons are tunable by twist angle, both in many different properties, resonant energy, lifetime, and diffusion behavior. But we start to ask, more sophisticated question as you start dope these systems, and can the excitons or the trions that can be treated as a tightly bound composite particle moving the smooth potential. As I mentioned, the bottom of the conduction band, the top of the valence band actually do not always occur in the same location within the moiré supercell. So this is a very naive picture that we all use in the early days. And also the fact that we realize as you twist and the layer try to achieve a tighter confinement, you're also changing all these other properties simultaneously. This is not desirable. So we were searching for a different way to impose moiré potential to localize carriers and excitons. So this is the new result that I'd like to share with you. So we started, for a lot of time we work on these layer of molybdenum bilayers, partially because then the optical spectrum is very clean. And in this particular example, my student Jida had prepared multiple twisted MOS-SE2 bilayers. As has been mentioned a few times, that these twisted bilayer at very small twist angle has lattice reconstruction that really dictated that lead to a complete commensurate AB and BA stacking within the domain and a high energy stacking AA domain walls. So only when you increase the twist angle, in this case, away from about 60-degree or H stacking by 2.5, we start to see this gradual atomic variation. I think this gradual atomic variation is important to also observe basically what Xiaodong has talked about, the interlayer pseudospin, lattice pseudospin variation. So experimentally, there's actually a very easy way to identify when the atomic alignment start to vary gradually is we look for these low frequency layer breathing mode in the Raman spectroscopy. And as you can see, even with a twisted bilayer, we don't always have the atomic variation in alignment. Only when we increase the twist angle to a certain number, this peak start to emerge, indicating now we have atomic variations. I think this going forward should be an important consideration when people are trying to interpret their results. And also in these bilayers, while the optical transition we directly probe are always going to be near the KK points, the doped electron hole may not be. In the hole doping side, the hole would actually reside in the gamma valley. So when we dope these structures, here's the intrinsic region. I like to compare the natural bilayer and twisted bilayer. I've also chosen to focus on this twisted bilayer where the atomic variation start to show up. And if we, on the electron doping side, you can't really describe the system with a simple trion, this excitation with a simple trion picture anymore, because there's a gradual energy evolution. So we started to adopting the language of polaron. I think there's some really interesting science associated with the electron hole pair coupled to a Fermi C. And then on the hole dope side, because the valence band is much flatter, and the holes are very much localized in the supercell at particular location. And we start to, in the natural bilayer, we'll have these, what we call the H1 trion, where the extra hole are residing in the same location with the exciton. But when we have the twisted bilayer, we were able to observe this additional trion state. So we attributed this additional trion state to a situation where the hole are sitting in a different location with the electron hole pair. We call them the charge trion, charge transfer trion, certainly taken inspiration from Stephen Lui and Feng Wang's work in this charge transfer exciton work. So these interpretation is supported by first principle calculation. This is a simulation calculation done by Li Yang's group at Washington, where when they look at the whole distribution, the whole experience a particular moiré potential and lead to highly localized hole at the AA stacking point. While if they calculate the exciton spatial distribution and observe where they are within the exciton moiré potential, there are two excitonic states that are quite energetically close. And therefore, you can form exciton at two locations and leading to two different type of trions. So I think these kind of picture could help to understand how you probe some of these localized hole or insulating state using optical spectroscopy method. Okay. So I'm now going to transition to a completely different topic. And I think although everybody, experimentalists all use hBN in our stack structures, and it's more recent that it's been recognized, there is ferroelectricity form in this twisted hBN substrate. I should mention that these kind of ferroelectricity is quite common for a lot of layer material as long as you break the structural inversion symmetry. Certainly they exist in TMDs as well. So let me just focus on hBN because everybody uses them. And there's a series of work, both transport and the scanning probe technique that proven when you have what's called a parallel interface, you can have boron and nitrogen vacancy aligned at the interface, and they if they're reversed, you would have two opposite electric polarizations that are formed. hBN are high gap insulators, but nevertheless, there will be small amount of charge redistribution at the twisted interface that's responsible to these spontaneous electrical polarization. So for us to get a large number of sample quickly, we actually use the folding method, and then we measure the electrostatic potential at the surface of this stack layer away from the twisted active interface using KPF, what's called a Kelvin probe force microscopy. So the results are here. There's a natural gradients in this of the moiré supercell in samples that are folded, probably because some residual strain, and that actually make a twist angle depend or moiré size dependent study simple. And we're going to define the unit cells and AB and with the BA domains with the A stack with AA stacking style as a domain wall, and the depth of the electrostatic potential we define is the bottom and the top in two adjacent domain wall. So these are the data. For relatively small domains, we can fit this potential variation with a sinusoidal function. And interestingly and importantly, it's to recognize that actually a pretty pronounced domain size dependence. So the potential, these data are taken with pretty thick hBN layers, 5 to 7 nanometers. If you make the hBN layer thinner, the potential will be even deeper. Even with this rather thick hBN layers, you can actually measure potential on the order exceeding 150 MeV. And I think this is actually still an underestimate because the tip is lifted a couple nanometers away from the sample surface. And this moiré domain size dependence in electrostatic potential is quite easy to understand. You basically calculate this is a simple theory done by Yao Wang's group a couple years ago. You calculate the charge redistribution and then simply do an integration and to find out what's the electrostatic potential due to that. The solid curve is not the fit, it's simply the theory curve that's plotted there. And here is an exponential dependence when you are away from the twisted interface. It turns out if the moiré supercell size B is relatively large, it does not decay very rapidly with the thickness dependence. Anyhow, so what we wanted to do is not use the ferroelectricity of the twisted hBN, so to speak, but we want to use the electrostatic potential to modulate adjacent structures. I should also mention another thing that's interesting and unique with this system is you can actually add up more layers. If you have the patient, just do 2 twisted interface, 3, 4, 5. However, the patient of the student allows, you would actually see if the twist angle is very similar. You simply add up the electrostatic potential. In this case, we're getting 400 MeV potential depth. And if the twist angle is very different at 2 interface, you have this multi-layer ferroelectric behavior with the bigger domain give you this larger triangle and this plateau in the potential, and with a smaller moiré give you the sinusoidal oscillation of the moiré modulation. So what can we do with the substrate? The most exciting thing to us is really now use it to modulate, put adjacent functional layer. And as I mentioned, when you twist 2 TMD, you actually are changing the conduction band, valence band in a very complicated way. But now you put a TMD, for example, on top of a twisted hBN, and each of the bands are modulated in the same fashion by the twisted hBN. That reduces the complexity, depends on what you're trying to do. And therefore, in some sense, is universal to all the different electronic bands in the system. And this is a calculation, again, done by Yao Wang's group. It shows a particular example. If we take a natural bilayer without twisting, place it on top of twisted hBN substrate with a supercell 25 nanometer. And now with the global gate, you can switch the bands of the bilayer graphene from a topological trivial to topological non-trivial. So this is another way, another example how we can use this modulating potential. We are far away from fully exploring this platform, but we just to begin with, did something simple we're familiar with and start putting monolayer semiconductors and show you that we can indeed reduce the diffusion of exciton and realize the localization phenomena. To be honest, there's the excitonic physics are quite complex. When we show this imaging in the published paper, we sweep a lot of things under the rug. What actually happens is actually there's a sizable lateral electrical field at the domain wall. And when we take a multiple spectrum across a sample with large domain that allow us to resolve within the domain and on the domain boundary, we clearly see double exciton peaks, and which turn out to the leading order likely just come from an in-plane electrical field that are causing a stark shift in the exciton resonance. And of course, you can put bilayers and different interesting materials and see what the moiré potential can do to these other functional layers. Okay, so I would like to end with some take-home messages. Our early studies and focus on twisted TMD layers, where we see a complex selection rule, resonant energy, light, and diffusion, all changing simultaneously with the twist angle. And when the lifetime gets long, it likely make these semiconductor inefficient light emitters. So we were searching for different ways to confine the carriers and the excitons that we come across the twisted hBN. I also like to say, besides the things we study and publish a lot on exciton and trion, when you start to couple electron hole pairs with a Fermi C, you really need to use a language of like polaron. And there are theoretical proposals, perhaps exciton can induce attractive interactions between the electrons. May not be a superconductivity anytime soon, but certainly you can expect some enhanced conductivity behavior in that. And we actually have some spectroscopy evidence that shows the bipolaron, essentially excitons are mediating attractive interaction for the electrons. And that's really for another day. And I'd like to end here, and then thank you very much for your attention.
I have two questions actually. First on the correlation. That means to make a domain wall with hBN.
Right. So this is something kind of different for the compared to the traditional ferroelectric. Traditional ferroelectric has almost atomically sharp domain walls. And of course, our measurement of the domain wall thickness is limited by the thickness and resolution. But so far, it's between 6 and 10 nanometer.
So that means if you get both
I think a couple nanometers are pretty much what we can do. You want the deeper, at least the first thing you would do to make the hBN thinner. Okay. Mm-hmm.
The last part you have is have you done power dependence at the boundary?
Do power dependence at the boundary? We have not focused on a power dependence.
So imagine you have the electric field that you can combine with initially they went down to the once you have electric field, you combine it. Once you're out, you imagine then you
right.
You may.
Okay, yeah, thanks for the suggestion. We'll look more carefully.
And it looks like that's on how very localized.
Yeah.
How localized are you? For example, one can envision this form some kind of escape space where on kind of predominant.
Right, so, like I said, even the twisted TMD with a small, it's like if you make the potential too tight, the wave function actually spills over. So you're searching for a compromise there. So we're actually not exactly sure, in this twisted hBN, we're not in the very small domain region yet. And where are they localized? We're not quite sure either. So potentially they're actually localized along the domain walls.